Alright, so welcome to the series of a few videos in regards to the subject of radioactivity. This is from the fifth week, the ninth lecture, and also it spills over to the 10th lecture with regards to implications of different type of radiations. We're going to start with explaining the forces acting within the nucleus. And this subject is super important to understand if you are doing a presentation, because Professor Vere will ask about different things that we will be discussing. Namely, if you don't understand the forces, there's pretty much no reason for you to give a presentation. And what are stabilizing factors in the nucleus? What are forms of radioactive decay? What is radioactive decay? And we're going to talk about alpha and gamma radioactive decays. And this is the time right now to say that if you're not familiar with what protons and neutrons and nucleus and isotopes are, I really strongly recommend you do so before we keep on going with this video. So let's get started. Let's talk a little bit about forces acting within the nucleus. Forces acting within the nucleus. And basically, we have protons, neutrons, and protons. These are our nucleotides in the nucleus. These are our nucleotides, and this is a nucleus. And just by counting real quick, and it's really important that I fix something here, a neutron does not have a positive charge as far as I know. Perfect. So we have 7 protons here and 7 neutrons here. So we're talking about nitrogen 14 isotope. Perfect. So we are going to discuss what forces are really acting on this nucleus. And there's one force that we know from everyday life, that is the electrostatic force. Electrostatic force. This is also called the Coulomb's force. Coulomb's force. And this is really the same force, the electrostatic and the Coulomb force. It's the same force. And instead of writing the equation of this force, basically what this force means intuitively is that if we have like charges, like 2 positive charges, or a different situation where we have like charges as 2 negative charges, these charges will repel. They would repel from one another, and we know this based on everyday lives. On the other hand, if I have a situation where I have different type charges, or let's just say positive and negative, and this is really the only scenario we have, these charges will attract. So like charges repel, and different charges attract. And how does this work in the nucleus? Where I already know that the nucleus is a very, very, very small space, and we have nucleotides very tightly packed, and I have these protons that are in a very close vicinity to one another, and they're all positively charged. And according to this law that I intuitively know, this force that I intuitively know in everyday life that works, these guys should be splitting apart. They should be repelled from one another. And in effect, I know that they're not. So there has to be some sort of other force in play here that prevents them from doing so. And that force is called the strong force, or the I'm just going to put it, the interaction, strong interaction force, or the strong nuclear force. Strong nuclear force. This is really all the same forces here. They're referred the same. If you're Googling this, or you're looking at different notations, different lecture notes or books, you will see this may be interchangeably used, but the strong force is the interaction force, strong interaction force, or strong nuclear force. What this force is saying, and again intuitively, it's saying that each nucleotide, either neutrons or protons, is going to have a very strong attractive force to its neighboring nucleons. That means that if I'm looking at this little guy here, this little neutron, it's going to have strong attraction force with 1, 2, 3, 4, 5, 6, 7 of its surrounding nucleotides. And this is a very, very strong force. Actually, the strong force is the strongest of the 4 known forces of the universe: the electrostatic force, the gravitational force, the weak force, and the strong force. And you can Google these guys up, but these are what we really need to know as far as what's going on in the nucleus. So what the strong force says is a strong attractive force. Strong attractive force between nucleotides. Nucleotides. Nucleotides being neutrons and protons. And the difference between, and it's a very essential difference between the electrostatic force and the strong force, is that we know that the strong force, being that we discussed here that it's only spanning the length of one nucleotide, it is a very, very, very short distance force. It's applicable for very short distances. So short distances, very short. I'm assuming that you intuitively know that the distance between one proton and the next proton is a very short distance. Whereas we know the electrostatic force from everyday life, we're talking about longer distances compared to the short force. Now what we have here is a nucleus, and we know nitrogen 14 doesn't spontaneously blow up, or we know that these protons do not part ways here. Do not go out of the nucleus. They're not spread apart. So the short interaction force must be prevailing. And this is basically what is going on. You can say that these two are components in a ring. The electrostatic force is continuously battling with the strong interaction force. These guys are continuously battling, and as long as the strong force is winning, just like in this instance, we will have a strong or stable nucleus. Our isotope is going to be stable. And whenever some of the environmental causes would cause the electrostatic force to be slightly more powerful at some point, maybe one of these protons is going to part ways from its respective compadres in the nucleus. So as long as the strong force prevails, we're going to have a stable isotope. Let's consider other stabilizing factors. And the number one stabilizing factors is basically the ratio between protons and neutrons. The ideal ratio between protons and neutrons is 1 proton to 1.6 neutrons. And that means that whenever I have an isotope that is close to this ratio here, it is going to be very stable. We can expect it to be very, very stable. Arbitrarily saying, if I have 100 protons and 160 neutrons, this is again very arbitrary. We know that this would follow this ratio, so we'd expect it to be very, very stable, just according to this ratio. And this ratio is important to know. It's often asked about, and this is what affects a lot of isotopes to a great extent, either being close to this ratio or being far away from it. And any isotope that is hovering around this ratio, slightly above it or slightly below it, we can expect to be more stable. Another factor that would affect it is the uneven or even distribution of neutrons and protons. And before I get into that, I'd like to credit Professor Verabes. This is from his lecture slide, this whole table here. He's from the Department of Biophysics and Cell Biology in Debrecen, and like I mentioned, he's the main man for discussing these topics. And he was probably your professor both in the seminar and in the lecture. Basically what happens here is that I see that I have the most amount of stable isotopes when I have an even number of protons and an even number of neutrons. Let's just say 30 and 26 for just arbitrary numbers. And I can also see that I'm going to have less stable isotopes when I have uneven or odd numbers of each. And I can see that I have the least stable isotopes when both are odd, when both are uneven. By odd, if you're not familiar with this, this means uneven amount, let's say 1, 3, 5, etc., etc., etc. So this is what's important to understand. This is another factor that would either condone stable isotopes or not. So perfect. As far as the factors contributing to the stability of the nucleus, we covered that, and it's super important to understand the ratio is really the main issue here. This ratio, and the further we are from it, the less stable our isotope is going to be. All right, so we covered the forces acting within the nucleus and the stabilizing factors. So let's start touching on the idea of radioactive decay. And basically, essentially, radioactive decay is a spontaneous process. This is a spontaneous process in which we would have a nucleus that for some reason is unstable. For some reason it is unstable, and would spontaneously, at random, it would decay into a different nucleus. This is called a daughter nucleus, and this is called the mother nucleus. So it would spontaneously decay into this daughter nucleus and emit constituents. And constituents are basically particles that are being tossed off of this nucleus, and it would get to the daughter nucleus, which is more stable. And I'm actually going to write more stable here. More stable, because it is possible that this daughter nucleus is also going to be unstable and keep on decaying, but it is going to be more stable than its mother nucleus. And an important idea to understand is that, being that we went from a relatively unstable state to a relatively more stable state, that means necessarily, by physical ideas, that we lost energy. So this also means that this energy difference was emitted here. Somewhere in this decay, energy was released. Energy is released. Energy is released. Very good, because we're going to a more stable state, which is less energetic, from an unstable state, which is more energetic. And if you're not familiar with this, essentially materials would gravitate towards the more stable, less energetic transition. And that's important to understand with the respect of what is radioactive decay: a spontaneous process in which an unstable nucleus would spontaneously decay into constituents and a daughter nucleus that may or may not also be radioactive. And this is radioactive decay. And we're going to start touching on alpha decay. And when we're thinking about, just very briefly, actually I'm going to go up and take a look at this diagram here. We can see that this guy in the middle, I'm going to switch colors here just to make it a little bit more obvious. This little nucleon in the middle has a lot of strong interaction forces with its environment, whereas this guy that is further away, this nucleon that is further away, has considerably less, which means that this guy, or this nucleon, has less strong interaction forces attracting him to his fellow nucleotides. And this is not very, very important when we're talking about very small nuclei like nitrogen. And consider what happens when we have a considerably huge nucleus. And how far is this guy going to be if it's in the far edge of this nucleus? And also consider this is in 3D, which means that if I have a sphere here, and there's a point in the middle that is going to be surrounded in all three axes with nucleotides, or a little point here that is not really going to be surrounded by much, it is a greater difference between a nucleotide that is inside and a nucleotide that is outside. Bearing this in mind, we're going to talk about what could cause alpha decay. And what I have here is I just quickly drew the surface of such big nucleus, and you can just imagine it continues on and on. And if I take a look at this, and I'm going to just put my charges on my protons, let's just assume that the strong interaction force at this surface area, and there's also surface tension coming into work here, but it's not super important. I'm not going to have very strong interaction force at this point than I would at this point. And just think of it as in 3D. The more dimensions you have, the more strong interaction forces you're going to have with your neighboring nucleons. Very good. So let's just assume that the ratio between protons and neutrons is very far from 1 proton to 1.6 neutrons in this nucleus, which would condone a less stable isotope, or there is uneven amount of protons and neutrons, which we also learned condones a less stable isotope. And at this point, maybe the electrostatic force would prevail over the strong force. And what would occur is that a chunk of this nucleus, a chunk here containing two protons and 2 neutrons, is going to be ejected off of the nucleus. It's just going to be thrown off, and I'm just going to to erase them from my nucleus here. I'm just going to erase them. So let's consider what happened. Let's consider what happened. I had a nucleus here that for some reason its constituents, its nucleotides, at some point the electrostatic force due to different factors of instability overcame the strong interaction force, and I had a little tiny piece of the nucleus containing 2 protons and 2 neutrons emitted out. And when you think about it, this, we know what this is. This is a helium nucleus. This is a helium nucleus, not to be confused with a helium atom. It's not a helium atom because it doesn't have electrons around it, so it's not an atom. It is just a nucleus that is just shot out with excessive kinetic energy. And when you think about it, let's just say that I had, just for kicks, 100 protons here. So that means that my atomic energy was 100, and I had 160, or rather I had, let's just say, 300 neutrons. And this is really arbitrary number. I lost 2 protons, and now because they were ejected out, now I have 98 protons, which means that I have a different element. The atomic number changed, so this is effectively going to be a different type of material now. And I lost also 2 neutrons, so I'm going to have 298 neutrons. So my new element is going to be the 98 type element, whatever it is. I'm not really looking at the periodic table, with less neutrons and less protons. And this is what it really means. The implications of alpha decay is that I am effectively losing from my total, if this is my mother nucleus, it is losing 2 protons and 2 neutrons, and it is turning into a daughter nucleus that is a different element because its atomic number changed by 2, and its total mass number also changed by 4 because we lost 2 neutrons and 2 protons. And this is important to understand. If you don't know what what the mass number and the Z, the atomic number, mean, I really encourage you to go through the basics of these things. And this is basically alpha decay. The emission of a helium nucleus, or this is also called an alpha particle, from a larger mother nucleus that has been rendered unstable due to various factors that we already went through. So this is alpha decay. And let's consider what gamma decay is, and I'm not really going to go through the extent of it because it's actually pretty simple for our purposes. Let's just say this is a part of my nucleus here. And what happens is maybe this nucleus would lose some energy in the form of these little guys. They may be vibrating or be shuffling around in some configuration, and energy is going to be released in the form of a gamma photon. And what's important to understand here, I'm not going to really go into the thick of things, but what's important to understand about gamma radiation is that gamma radiation is nuclear radiation. And you would say, oh, this is obvious that it is nuclear radiation, but I'm only saying this with respect to the difference gamma radiation has with X-ray. And the only difference between gamma and X-ray, well, you may say, oh, gamma is more powerful than X-ray because it's in the far end, but actually hard X-rays are just as powerful, could be just as powerful as gamma rays. So the difference is not essentially the frequency or the energy, because hard X-rays could be just as powerful. The difference is the source, whereas the source for gamma radiation is nuclear and the source for X-ray is electronic transitions. And if you're not sure how X-rays are generated, maybe it's a good time to review the videos on that. And this, I'm only mentioning this because this is often asked about. So it's important to know. What's also good to know about gamma radiation, or gamma photons, that it accompanies virtually all types of radiations. It accompanies alpha, and beta positive and beta negative radiation. We will also, in these cases, see an emission of a gamma photon, which means that after this guy was emitted, maybe right along with it, it was this nucleus would emit gamma radiation or a gamma photon, or maybe this gamma photon is going to be emitted slightly after this particle is going to shoot off. But in any instance, gamma is going to be associated with the decay of this particle here. But basically, when we talk about gamma emitting isotopes, it can be through all these types of decays. But initially, we're talking about the only thing that this nucleus would emit as a gamma radiation. It would not emit alpha or beta, all these things. So this is a gamma emitting, gamma decaying isotope. But it's good to know that gamma really accompanies all types of decay. It's kind of good to know, but when we're talking about alpha decaying isotopes, we're not really referring to the gamma energy that is released. When we're talking about beta negative decaying isotopes, we're really not referring to this gamma radiation. We're talking about the constituents, the alpha or the beta particles that are emitted from the isotope. So that's our focus. So we went through what radioactive decay is, a spontaneous process. We mentioned that due to various reasons, the nucleus could be rendered unstable, and an alpha particle containing 2 protons and 2 neutrons can be emitted out of the nucleus, and it would change the atomic number by 2, and it would change the mass number by 4, because we're losing 4 nucleotides and we're losing 2 protons. We discussed that gamma radiation virtually accompanies all types of decay, but it could be a point where it is the only type of energy released due to shuffling. You can say shuffling. I've heard it referred to as shuffling of the different nucleotides and energy loss within them. So this is the basics of radioactive decay, and we're going to go through the different types of radioactive decay in the next video. So I'll see you then.